Good evening, everyone. I want to thank Camille for that wonderful introduction and to thank all of you and say how much we're watching you. The state of Washington is very interested in how states are solving the problem of not only K through 12, but early learning. And we have our own early learning advocacies in the state legislature. So every time you make an advance here in California, and I'm talking at the state legislature, I will remark on the fact that you guys are making progress down here, and we better get on it to make sure that we make timely progress. So give yourself a hand. So I'm here tonight to share with you some of the latest research on early brains and how they develop. And I hope that it's going to arm you with a lot of evidence that says that we can't stop with educating the 4- and 5-year-olds, that we really do have to bring the early learning movement to the entire United States. We have to care about every single child because the capacities of children to learn in that early period are truly phenomenal. One of the messages I want to give you tonight is that babies come ready to learn, but that you have to build a brain. Brains have to be built. Brains are ready for learning. They're ready. They have the opportunity to learn, but we have to provide it for them. The architecture of the brain is built during that early period. Why do we know that? Because we've got first in the world measures of brain function now. I'm going to show you films of little babies in very big machines that allow us, without any invasiveness, to measure what's going on inside the brain as the baby hears a word, sees a photograph, recognizes their mother, or hears music. We can now look inside and create a movie that tells us what's going on. We also can look at brain structure in a way that we've never looked at before. We can color code 1,000 areas. You see about 150 there. And the bushy, I'll show you later, the bushy connections between the brain areas, like superhighways in the brain, that allow various specialized areas to talk to one another. So the brain science is coming to a place we've never been at before, and particularly in that period 0 to 5. And the reason this is important is because it lays out for us the foundations of how children learn, how brains grow, what it takes to provide the brain what it needs. And what's exciting about the work that we're doing is that it demonstrates that every single baby born on the planet has the same capability at birth to learn in this way, unless there are only 2 exceptions. If the mother has abused alcohol or drugs during pregnancy, that baby's brain is not ready in the same way. But every other child is ready in that way. I think that's so enormously hopeful that children have this capacity and every single child has it. So let's take a tour through this data set that we have and try to understand what it is that little ones are putting to work that we can't. Our brains, in a way, cannot work with the flexibility and broad openness that we see in very young brains. Why is that the case? Well, let's look at a very simple statistic. I think most of you have seen this already. This is just a measurement of how large the brain is. It doesn't say what's going on inside, just how big is it at particular ages. So isn't it impressive that by 1 year of age, that brain is 70% of its adult size? And by the time we send our little ones to school, 5 years of age, 92% of its adult size. That's amazing. It isn't that we reached adult size, in the teenage years. It's really in this early period. So if you were the decider, if you had data like these in front of you, wouldn't you feel as though it should be an important time to invest in the growth of that brain, given the degree to which it's growing? Well, okay, so this is just a bulk measure of the size of the brain. What's going on inside of it? Again, this is one you may have seen before. The connections between brain cells, neurons, have to be forged. We're all born with trillions of neurons, and we have the same number of neurons at birth that we have almost throughout our lives, because that's when you have them, early in development. You're not really constantly growing new neurons. You're growing some connections, but you're not creating new neurons. What you are doing, though, from that beginning period is to build connections between each of them. It's as though you've got houses with no telephone wires. And so in order to communicate, the houses grow telephone wires between them. So that's what's happening in the early years. And by age 3, the baby has 3 times the number of synapses. Those are the connections. You know, they grow towards each other, and there's a synaptic junction where the electrical pulses can jump over. So by the time a child is 3, they have 3 times the number of synapses that you and I have. And then between that early period, about 3, and at different rates throughout the brain, there's a systematic pruning. So that by the time our children are teenagers, by puberty, that brain is more like ours. It's been pruned. And that pruning builds a strengthening, just like a rose bush. Why do you prune a rose bush? Because if you don't, it has many spindly twigs, instead of pruning properly, in which you get very strong branches. So the brain is exactly the same. You have to prune. Parents often ask me at talks, what can I do to make my baby's brain not prune? And I say, no, that's not what you want. Every brain will prune, and pruning depends on experience. You prune what's not been used. You prune what's not needed. So pruning is an important thing. So keep in mind, you've got the baby with trillions of neurons. Then you're going to build these connections, 700 per second. Connections are built in the early period, 700 per second, and then they're radically pruned. So that by that time, by the end of the teenage years, you have a kind of an adult brain, Yeah, well, we know. We're not going to talk about the teenage brain right now. That's the second most fascinating period in development. But it is amazingly different at the end of puberty than it was at age 5 or age 7, and all of us prune differently. The reason we're all so unique as adults, we have very, very specialized brains, because our connections and everything that we forged, that architecture in development, depends upon our lives, our inheritances in terms of our genetics, and then the epigenetic folding of the experience sculpting the brains that we're now walking around with. So look at this change, birth to 3 to age 14, and now look at a learning curve. Biologists often show this curve. It comes from psychology, not biology. Biologists who study animals know that there are critical periods for learning, that animals don't learn at the same rate throughout their lifetimes. There are special opportunities for the visual system to get wired so that you can see, binocular vision. The most important period that's been verified in humans is the one for language learning. That if you look at your age on the bottom of this curve and then find your skill level on the vertical axis, you'll see that the babies and children are geniuses from 0 to 7 at learning a second language. And every 2 years after the age of 7, there's a decline. And then after 16, there's a big drop. After puberty, the huge change in your ability to learn a second language. So why would that be the case? Of course, when do we try to teach second languages to kids in the United States? In high school, we're fighting their biology. Whereas the first 7 years, and I'll show you some of what goes on, they absorb language. They could absorb many languages. And we'll talk something about that before the end of the evening, about what bilingualism, what knowing 2 languages does to your brain. Very, very good for the brain. But in America, we haven't learned that lesson. We are afraid of bilingualism. But all of the rest of the world, most of the rest of the world, has demonstrated how easy it is. And I'm doing a special project in Madrid. I'll tell you about that in the end. So we've been interested in what's the magic that the kids from 0 to 7 are applying to learn a second language. We think it's going to tell us something about the entire baby brain. How do babies approach learning in a way that you and I don't approach learning anymore? What are they doing that you and I can't do? So we began some decades ago with a behavioral task going all over the world. I had laboratories in 8 countries at one point. And I was taking a behavioral apparatus to try to test how do babies do the first thing they have to do in order to speak. They have to know how to make words. And in order to create words, they have to know which sounds are critical. Every language uses about 40 different sounds to create words, and different languages use different ones. So how do infants learn which ones are important? Can they even hear the differences? The difference between pat and bat is a small little change, happens in about 30 milliseconds. Can babies even hear that distinction? Well, here's a task that we invented. You'll see a baby sitting on a mom's lap, and she's watching someone play with toys to keep her attention to the right, and there's a loudspeaker on the left, and when the sound changes, her job is to turn her head. She's got 3 seconds to turn her head so that she sees a toy in a box, but she can only turn her head to see the toy when the sound changes. So let's have a listen and see how she's doing.
Can a baby as young as 6 months old hear the difference between two vowels? This baby is trained to look for the toy when the sound changes. She's being distracted, so she'll turn only when she hears the difference in sounds. The key question, will she turn before the toy lights up?
Okay, she knows how clever she is. And so we learned over about a decade that every baby in every country of the world could hear the distinctions between every sound in every language. There wasn't a single sound contrast that we tested that babies at this age, at 6 months, couldn't hear. Now the moms behind them, okay, or the dads who came into the lab, were only good at hearing the distinctions in the language they'd been exposed to, or if they were bilingual, in 2 languages. But the babies could do it all. They were citizens of the world. And we were shocked by that result. These are very, very small differences that they were paying attention to. But there was no doubt many laboratories demonstrated this same phenomenon. But the babies were citizens of the world, and you and I no longer are. The mothers and fathers sitting behind the babies and holding them were not. So we began to ask ourselves, what magic is going on here? When do the babies turn from their citizen of the world status into us? We're language-bound listeners. We are really dedicated to the language, the words, and the sounds that we use, but are unable to hear an Urdu contrast or a Hindi contrast. It's part of the reason it's hard for you to learn a second language, is that you can no longer hear the sound contrast. So when do you think babies change from citizens of the world to the culture-bound listeners? Well, it turns out they change by their first birthdays. Between 6 months and 12 months, every little one across the planet was changing from that universal citizen to a child who was very, very good at the distinctions they were hearing mom and dad use in words, even though they couldn't understand words. They were very sensitive to the sound contrast, and failing then on the language, the sounds from languages that they were not exposed to. So between 8 and 10 months, that was the biggest change. By 12 months, every single child had changed. The degree to which kids are able to do this in that 6-month period predicts language growth till the age of 3 and reading readiness at the age of 5. It's a very sensitive measure. And now these behavioral tests have been supplanted with brain measures, and the brain data, of course, show the same thing, except now we can see what part of the brain is actually doing it. Babies are born in this very universal stage, and then there's a kind of pruning going on by the time they get to their first birthdays when first words occur. So what is it that they're doing? What's the magic? How are they learning when they can't understand words? So there's 2 principles we've identified, and it's true not only for language, but for learning more generally. The first is that the babies are statistical learners. So think about a statistician. A statistician takes account of numbers. Babies are very sensitive to the number of times an event occurs, not just a sound, but what they see, what they hear, what they feel. The higher the count of a sound in their language, what you present to them, the more they're likely to hear it as distinct from others. So in 2 minutes in the laboratory, we can maybe make a baby hear more like a Japanese baby than an American baby by reducing the number of R's and L's they hear and increasing the number of that Japanese in-between sound, the Japanese R. And we can make Japanese babies hear more like American babies if we play them lots of R and L sounds. So they're like frequency detectors. The brain, regardless of the words that they don't understand yet, they're taking account of the number of sounds. Now, it's a little frightening to understand that this works not only for sound, but for sights that they see, for actions they see, for music they hear, and for all kinds of other events in their lives. So this frequency detector that babies are means that we should be careful what we put in front of babies, right? Because they're paying attention. They're taking statistics on what we do. But in addition, so that's principle one. Babies are little statisticians. So be careful what you put in front of them because their brains are taking into account the frequency of the things they hear, see, and actions that they see you do. The second piece of it, though, is that babies' brains in their statistical mode need a social context. So they're not just taking statistics randomly. They're taking statistics when those statistics come from people. So when in the presence of a person, babies will take statistics on a new language. And we proved that in the experiment you see displayed here. We ran an experiment to see what if you exposed an American baby in Seattle to Mandarin for the first time, Mandarin Chinese, or to Spanish. This is the critical time for them to learn, but they haven't been listening to Mandarin or Spanish. Are they capable of taking statistics on a new language? So on the left, you see the live exposure. We brought in, I had 6 graduate students who spoke Mandarin as their original language. So 12 sessions between 9 and 10 months, babies came into the lab, and for 20 minutes, they listened to nothing but Mandarin, games and toys, books and toys. And on the right, you see the other condition. We had, at the time, there were tons of software products on the market. So teach your baby French or teach your baby Urdu or whatever with this wonderful baby video. So we ran a condition, made beautiful DVDs. In fact, the graduate students said, those are so gorgeous, those are so good. The babies are going to learn better because it's less chaotic, It's simpler. So I'll tell you what happened, but first look at what the live session looked like. So listen to this. Okay, so how is your Mandarin coming along? Okay, the babies were riveted by these conditions. On the other hand, the kids who watched the television set also seemed to be riveted. They would crawl up to it, some would kiss it, some would touch it. They were very, very attentive to these 12 sessions, run at the same dosage, same time, same room, same everything, but on a DVD, on this beautiful screen, as opposed to in the live, more chaotic kind of setting. What did the data show? So after 12 sessions, all the babies went through the brain imaging study, and we could see what's changed, and also the behavioral task, that head-turn task. What we demonstrated was that the kids in the live group were so good that they were statistically identical to the kids in Taiwan who had been listening to Mandarin for 11 months. Whereas the kids on the right, who had stared at the screen, learned absolutely nothing. They were equivalent to the control group who had been exposed to the American graduate students, same books, toys, but speaking in English. So this social delivery of the new language allowed babies to take their statistics, whereas the other condition, it isn't just rolling across the babbler membrane. It wasn't just hearing language that caused them to take statistics. It was the delivery through a social human being. We have learned in many of our studies the key variable to the baby brain is the social context. Babies need a social partner. Their brains are born to learn, but they need a delivery system that is us. They're riveted by our faces, by our language, and by our gestures, and they take their cues from us entirely. So that social piece we can actually see in the brain, and again, I'll show you in a minute, what does it look like to see social areas of the brain light up as a child listens to speech? So these experiments demonstrated to us not only the extraordinary learning capacity of young infants, but the importance of a social context, the importance of actually hearing language from people in that early period of life. And that, of course, reminds you, I'm sure everyone in this state, probably everyone in this room, has heard of the 30 million word gap. Now, this is pretty old data. This is from Hart and Risley in 1995. In 1995, we knew this gap existed, that by the age of 4, if you counted the sheer number of words a child had heard who grew up in a professional family, a working class family, and a welfare family, that the number of words they heard was vastly different. So people began to understand, what is the achievement gap? What is the preparation gap about? If the brain is ready for language, if the brain needs a social context, then what children need is to be read to be talked to. And that's part of building the architecture that's going to take that child from the crib to a child at 5 who's ready to read. And if they're not talked to, if there's not that sort of social engagement on the part of the parent and child, that's not going to happen. Our most recent brain studies are demonstrating that at age 5, you can measure children in terms of their language, cognitive, social abilities, and take measures of the socioeconomic status of the family. And then look at the brain and say, what measure predicts the brain's integrity? What measure predicts the brain's skill? Socioeconomic status of the family is the hands-down winner of predicting brain function at age 5. Not so much the children's skills. They are competent in terms of their cognitive, linguistic, and social skills. Not so much so that that variation doesn't predict brain variation. What does is socioeconomic status. What does that mean? It means that SES is a proxy for opportunity to learn. The brain is born ready to learn. Children are born curious and ready to learn, all of them. But without the opportunity, the brain doesn't develop that architecture and that sophistication. Our most recent studies on language input to children show how important quality is. I wasn't going to show you too many graphs tonight, but this is a knockout effect. We measured at home using little recorders that the babies wore, little Lena recorders, the little 1-ounce recorders with very high fidelity. Babies just wore them 24/7. And we could tell everything that was going on in their auditory worlds. How much television are they watching? How much radio have they got on? How much face-to-face conversation? And is that conversation parentese or is it standard adult speech? So how many in this room have heard of parentese or motherese? Okay, quite a few, but not everybody. Parentese, motherese is the kind of style of speech that we use when we talk to a little one. So I'm using standard adult speech. It's not as though there's no variation in the fundamental frequency of my voice, but if I had a 2-monther right here on my arm, I'd be doing something like, hello, how are you? Let's open up those big blue eyes. Okay, it's slow, it's very intonated, and it's got this sort of high frequency average pitch that babies love. If you give them a choice between parentese, it's called parentese because now we know men do it and grandfathers do it, as well as grandmothers and mothers and siblings of older siblings of little kids. So this parentese style of speech, when you pit it against standard speech for a little one, for a little baby, they'll do whatever they have to do, turn their heads, kick their legs, to turn on that parentese speech. They love listening to it. It's slower, it's more melodic. It's easier for them to talk back to, which is really important. We recorded in the homes at 11 months what's the prevalence of parentese, particularly face-to-face parentese, as opposed to standard speech face-to-face. And what we showed is this graph of words produced at 24 months. So on the right is standard speech. Standard speech is flat. It looks a little negative, but it's not a statistically significant effect. If you're speaking standard speech to your child, you're not building that words produced outcome measure at 24 months. But if you're producing parentese, that line's going straight up. The more parentese is spoken in the home over that 4-day period that we recorded, the higher the number of words at 24 months. And this is a knockout effect. I mean, it's like 433 on average words for high levels of parentese to 169 words for low levels of parentese. This is the kind of talk that kids need. It's the kind of talk that makes children know you're engaging them. You're attending to them. You're in front of them. And that's what the brain loves to see. So I've been talking brain, brain, brain. How do I know? Look at this machine. Now this looks like a hairdryer from Mars, doesn't it? Okay, it's the only device in the world that is safely, non-invasively recording brain activity in any sized individual. We happen to be the first in the world who put a little one, because it was perfectly safe and non-invasive, this is a 6-monther, in the big machine. So a little baby in a big machine allows you to, you can see, it's a technical tour de force, and I won't even be able to give you all the details, but the cool thing is that she's moving. It's not noisy. This machine is on. She's listening through insert earphones. So I can show you how quiet this machine is. It makes no noise. It's picking up magnetic fields in her brain through that device that you see. That helmet has squids in it, superconducting quantum interference devices. It's picking up magnetic fields that leak from our brains as we think. Right now, if you're thinking, there are magnetic fields leaking from your brain. And what we can do is give the baby a task and measure what's happening in her brain, and we end up with a movie with millisecond precision and about 1 millimeter precision in terms of the spatial resolution. And so it's just a technical advance that is allowing us to do an enormous number of things. I'm going to show you the first movie that we produced. What we were doing is presenting to the child words in Spanish and English. This is a 12-month monolingual child. So that 12-monther has already kind of narrowed to English, right? And we want to see what's active. Of course, the auditory system has to be active, but what about the social areas? What about Broca's area? Important to reading, important to social interaction. So here's the movie of that. This is an individual 12-month monolingual child, color coding 150 areas. We're focusing on 2, the auditory areas. It's an auditory stimulus. It's got to light up that area. And Broca's are those the blue lines pointing to it. There's the connecting wiring between, that's the arcuate fasciculus connecting those 2. The red bubbles are the firing of neurons in the brain, millisecond by millisecond, as the child's listening. The surprise is this. Auditory areas, of course we expected auditory areas to be lit up, but Broca's, that social area, that, attempting to talk back, it's the motor area that allows you to respond. As I'm talking, our studies are showing, as I'm talking, your brain is working through Broca's to imagine what you would say if you could ask a question, or as you're trying to remember what's going on that's important. You're working Broca's area. So is the baby. At 7 months, we observed this kind of activity. It was equivalent for Spanish and English at 7 months. The brain doesn't know the difference at that time, meaning English is coming in or Spanish is coming in, Broca's is trying to work it. What would I say back to that? How do I do that? By 12 months, when Spanish is not the native language, English becomes easier for Broca's. If Broca's is getting ready to talk back, English is a snap. But if Mandarin comes in or Spanish comes in, that Broca's area is working doubly hard and doubly long, trying to figure out what would I say in response to that. So the shocking thing here, I think, is the fact that this baby brain is engaged. When you play non-speech kinds of signals, you don't get this Broca's activity. So Broca's is trying to register something's come in that I want to respond to. It's a social response. It's the engagement that we need in our babies. So for the first time, MEG technology is allowing us to create these kinds of movies. We're working on all kinds of things, and I'll only be able to mention a couple of them tonight. But one of the things I wanted to make sure to mention is that look at this connective tissue. We can now image the superhighways running between areas. So if Broca's area is specialized in motor movements and social, and the auditory areas are listening, and the visual areas are taking care of your visual system, what's allowing them to communicate with one another? Like a business that has specialty areas, you've got to have a way for those special areas in every one of our corporate companies to talk to one another. Here's the baby's solution, our solution too. This is the wiring in the baby brain by 12 months. It's incredible the degree to which the wiring has been formulated by 12 months. So the pathway that I showed you a minute ago that connects your listening area to Broca's area is this blue coated in the middle called the arcuate. Now, the arcuate is very critical for learning to read, and I had to show you this because this is our youngest assistant professor, Jason Yateman from Stanford, just joined us at the University of Washington. What he's demonstrated in his studies is that if you measure the arcuate and its growth, you can predict when a child is ready to read, ready to learn to read. You know, we've been saying that kids should read all at the same time, and we've been acting as though every brain is the same. And when a child doesn't read, we act as if something's wrong with Johnny, something's wrong with his home, something's wrong with Johnny, Johnny can't read. The truth is Johnny's timing is not the same as Sally's and Fred's. What Jason has shown is that if this arcuate has already formulated, it's done its growing, when reading instruction comes in, it's too late. On the other hand, if it's not started its growth and reading instruction comes in, it's too early. There's a perfect timing for every child. As the arcuate is growing, if reading instruction comes in, it's like magic. It really, really develops. It takes. So I want to plant the idea that what we're heading to over the next decade is something called personalized neuroscience. And every child will have the benefit of this. You know the phrase personalized medicine. We know all of our livers are different, our colons are different, and our needs are different with regard to how we eat and how we sleep. We've come to our doctors to say, give me a formula that will be best for me. I want to be the healthiest I can be. We should feel the same way about children's brains. We will be able to give advice that's not cookie-cutter advice. Every child does this at 3, every child does that at 5, every child does this at 7. Reading has been contentious since day one. We're going to find that reading can be optimized in every child by understanding how the critical circuitry in the brain that's responsible for reading is developing in that child. So not today, but within 5 years, certainly within 10, the kinds of measurements we're taking with big machines will be made with simple sensors. We'll have known where in the brain is that activity taking place and what does it look like. Then with simple sensors that you could put on the scalp, we'd be able to measure these kinds of things in offices, maybe even in schools someday. So I think we can look forward to the kind of learning that would benefit every child, that we should think about every child being able to read and every child being able to reach their potential. So one of the other concerns that America has to have, that the rest of the world is running far ahead of us on, is the creation of a bilingual brain. Now, we've done lots of studies to show, and Europe should have convinced us, and Asia should have convinced us, that the kids who are exposed to bilingual language in the right form, meaning they're hearing 2 languages all the time, that their word development, their sentence development, their sound discrimination, it's all happening wonderfully. If they're getting the right input, they're doing perfectly well. But the news is that they have a benefit, not just that they know 2 languages, they're actually more cognitively flexible. So what do I mean by cognitive flexibility? Here's a couple of our subjects. Cognitive flexibility means that when you're faced with a brand new problem, that you're better able to invent a new solution, okay? You're better able to decide, I'm not going to go the old path, I'm going to take a new path. So how do we test babies? We've demonstrated that babies who are bilingual are more cognitively flexible. So here's the task. Here's a little 11-monther who's a monolingual. She's sitting at a table, sitting on mom's lap. She has a plexiglass box, and we put a toy in the box, and she's allowed to pull it out. But only one door is open. So she has to learn, I have to go this way to get the toy out. And then we turn the tables on her, so to speak. We reverse the box. She has to invent the solution. Oh my gosh, the old door is closed. What am I going to do? Just like us, when we tend to think, I'm going to use the old solution, even when you need to invent a new one. Okay, so watch what happens. Here she goes. The toy's coming in on the left, and she's going to pull it out. Every child learns how to get the toy out of the box. That's not a challenge. And we let them do that about 6 times, so they've gotten very used to pulling it out through that door. But now we're going to turn the box around, and they see us turn the box around. They see the toy go in the other side. But it's hard. This is a hard problem. So most of them push on it, look, so she's going back to the old door and wondering, why doesn't that work? All right, so she doesn't solve the problem. Here's the bilingual child, same task. Toy goes in on the left. And they all push it. They all think pushing will make it pop out or something. And she finds it. It's a great treat. They love the toy. Okay, so same conditions. Turn the box around, get the toy back. It's sometimes hard. Okay, so there it goes. And we get a little pushing, and a quick look to the old side, and then this understanding. Isn't that amazing? Okay, so the statistical result is they're twice as good. The bilingual children are twice as good at 11 months. Bilingualism is really good for your brain. It exercises the prefrontal cortex. You get used to switching all the time between language 1 and language 2, and that's like lifting weights for the prefrontal cortex. It's what allows you to direct your attention. It's executive function, the beginnings of executive function. If you're a bilingual, you'll cognitively age less fast. You'll be a better, I can see a bilingual cheering back here, and you'll be diagnosed with Alzheimer's at a lower rate. So it's very, very good for your brain to be a bilingual, and even for the babies. So I want to end with 3 interventions that I'm convinced will help our children. One is that we really can connect the dots between the crib and being able to read at age 5. It's especially important that low-income families who don't have the opportunities, don't understand the need for the opportunities, we know exactly what to do, that we can connect the dots, we can coach people to do that. We're engaged in these kinds of language building skills. The second is that I'm creating bilingual babies in Madrid. One of the problems that all of us have is that if we don't speak our second languages, how are we going to give the second language to our children? Madrid's parents were saying the same thing. The Ministry of Education brought me in. The advantage of Madrid over the United States is that 60% of the babies at 4 months are in their nursery schools. Subsidized by the government, every parent pays what they can afford. By 3 years of age, 100% are in. That's mandatory by age 3. And these nursery schools are fabulous. When I saw them over a year ago, I thought I'd died and gone to heaven. And the ministry said, parents want their children desperately to be bilingual, but they don't speak English. Can you think of a way? And I said, I know how to do it. I brought 16 University of Washington undergraduates to spend their junior year abroad to 4 schools in Madrid. We created a randomized control trial. So half of the children are in the control group, half of the children are in the experimental group, and get 1 hour a day. We have 3 different age groups, 1 hour a day of English play, songs, reading, talking, all very playful. The first cohort is just out. We had to flip the groups at the halfway mark because the parents in the control groups were up in arms saying, we want our children to have the experience. So we finished on February 1, the first cohort, and we're analyzing the end results of the first cohort. We've flipped the groups, and so now the experimentals are controls, and the controls are now in the bilingual classroom. But they appear to be learning like crazy, just absorbing it like a sponge. When we get the results, I think the entire world will pay attention, because wouldn't we love to have the magic for our children to expose them to second languages? If the schools can do it with 1 hour a day, that would be news. So we'll await the results. In a couple of months, we'll know. The third one, and then I'm going to end on this, what programs have been cut out of schools more than anything else? I think music and the arts. Okay. We believe that pattern stimulation, not just language, but all kinds of activities that we put in front of our babies, it's making a difference to their brains. Their brains are building architecture based on what we put in front of them. So we gave babies, at the same time that we had given kids, Mandarin exposure from 9 to 10 months, we said, what happens if we expose them to music? We brought them in social groups and let them listen to various versions of the waltz. 12 sessions over a month's time, brain tests after exposure, and we're now tracking language development until age 30 months. I'll show you in a minute what those films looked like, but what we demonstrated was that 12 sessions of listening to the waltz not only made babies better and their brains keener in their sensory areas, you know, the auditory area, when you violated that rhythm, babies got used to bump, 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 the timing of a waltz. All you had to do was move that second note by 10 milliseconds, and the brains of the babies were completely reacting to the violation in the rhythm. But it wasn't just for music, it was for speech. Foreign language contrast, a rhythmic contrast. The babies had learned something about the pattern. And the brain evidence demonstrated that sensory areas were more sophisticated in these exposure babies as opposed to the control group, but their prefrontal cortex. When you have patterned experiences, you learn the world is predictable. So let's learn those patterns and get ready for them. That's what our worlds are like. Get ready for the patterns. Try to understand what the world's about. And that's to be distinguished from a child who's raised in a chaotic household, under toxic stress, under conditions of abuse or neglect. The kind of children who have very little executive function. Why? Because patterned experience, the only pattern was the fact that I might get hit, or I don't know when I'm going to be fed next. There isn't a world in which you can predict the patterns. Patterned experience gives us an idea, and the brain results we saw gives us an idea of why early experience is so very potent, because architecture is built based on those experiences. So I'll end with a little session. You'll watch the babies listening to Take Me Out to the Ball Game. See how they watch each other? Anyway, I thank you for listening. So I heard there might be some time for questions, and I hope there still is. I think there may be some burning questions out there. Oh, a microphone, that makes sense. Okay, good. Thank you. Yeah. Okay,
We're going to go sit down
okay. Sounds
over
good.
there in those chairs. Can
All
you
right.
give her another hand? So my burning, can you hear? Is it on? Good?
Yeah.
My burning first question is, can I go to Madrid? Wouldn't that be the most fun
Yes,
thing?
you can. Oh, they're having so much fun. They're having so much fun. The undergraduates are learning about the brain, learning about children. We've got equal numbers of men and women going, and the kids are in heaven. In fact, the Madrid teachers are watching our undergraduates saying, why are the kids coming out of the bilingual classroom so happy? They're singing and, because it's playful learning.
It sounds
It's the
great.
way we were built.
Yeah.
We are built.
Yep. So my apologies, I didn't announce in the beginning that we would have questions and answers, so we didn't pass out the cards soon enough. But we do have a couple of mics, so if you have a question, raise your hand and a mic will come close to you. But we're going to start with a question that we have, but then the mics will get there. And our first question is, how have policymakers in Washington responded to your findings on early language acquisition?
So I've been to 2 White House conferences, right? Hillary Clinton's in 1997 and the Bush's in 2001. Actually, Obama had one a couple of years ago too, and I was at that one. I think at the federal level, there's a great deal of desire to put this knowledge to work. Everyone wants evidence-based programs. The problem is the states are the ones that need to enact legislation and provide the funds. So while you've got, it's very, very important to, in fact, I was so naive in 1997 at the first conference. I came home thinking it was all going to be solved. I mean, you'd spoken to Congress, and they were excited about the potential, and we didn't have anywhere near what we have now. But it didn't solve it. And now every state, you guys, we're all watching you. I think California, as the senator said, 7th most largest economy. We're watching states who seem to be making some headway. Washington State's making some headway. That's where it has to happen. We have to believe enough in the children to somehow make it work. And it shouldn't be a zero-sum game, but it oftentimes is. We are going to have to save money to produce the kinds of programs for children that will save us money in the long run. I know Jim Heckman's been here to talk to the water cooler group. And it's just, there's no doubt you save money by investing in the early period. And it lasts. If you follow the abecedarian kids at 27 and 35, those groups can still be distinguished based on their income, their holding down of jobs, their failure to end up incarcerated. I mean, there are measures that show early learning pays off. So it's not only the economic argument, it's the moral imperative. Every child has the capacity. Right. They have to have the opportunity, though, because brains need to be built.
Okay, going to the audience.
Hi there. I think it's me.
Can you stand up?
Yeah.
There you go.
There you are.
Hi, I visited the New Orleans Nanny College in the UK, and I was surprised to see how different the care was for the children, how low the ratios were, how well paid each of the nannies were. Could you tell us something a little bit about Madrid? You said that the babies are in the nursery schools as young as 6 months old, and everybody by 3. So can you talk to us a little bit about the workforce there, about the environments and the investments that you see being made in Spain?
Right. So the workforce has some training. It's not a degree program as I understand it, but there is some training required for everyone who is in these nursery schools. But they're really, really fun nursery schools. So they personalize, every child brings in their own nappies and they have their names, their favorite toys are brought in. And the kids are in a social setting all day long. They're fed together in tables where they have the practitioner in the middle of a kind of round, and they're either high chairs around or they're baby seats around, or when they get to be 2 or 3, they're sitting in little seats. So they do everything socially. There's a lot of language, there's a lot of play, talk, and social activities and physical activities. They just believe that the children are going to be better off in the long run if they all have the opportunity to be in a school where they're well cared for, and as I said, parents pay what they can. So it's a belief on the part of the Madrid with their 6 million kids that that's the best way to bring up the children.
Great. There we are.
Hi, I have a research question. On your musical one, I noticed there was kinesia, they were doing
They were
physical,
doing this.
And there was also social. If you did music without social, would it have the same kind of blank effect as language without social?
Right, so we don't know that yet. We designed this to give it its best shot, right? So we actually believe our brain research and everything else we're doing says the social brain is the gatekeeper to learning. The more we understand that you get into a brain through social, a child has to understand that it's interesting, that it's coming from a human being, and that it's part of the culture. I mean, how is it that a child knows how to negotiate the world other than by paying attention to what other people do? Imitation is such a strong mechanism. Our value systems, our cultures, our language all come through the social channel. And we used to think that the right hemisphere does kind of social stuff, soft stuff, and the left hemisphere does logic and mathematics and language. That's not, when you really look at brains operating in the real world under these kinds of devices, whether it's an adult or a child, the entire brain is active. The social brain is active no matter what stimulus comes in. The social brain is deciding whether it's important, and the prefrontal cortex is deciding to pay attention and directing the attention. So everything's active. Social, attention mechanisms, and then the sensory system that's being operated. So vision or audition or haptic. So it's sort of nonsense to separate our kind of emotional side to our intellectual, cognitive side. It's really a blend. It really is a blend. It matters how we feel about things. So emotion and social is the pathway, and it's absolutely essential in childhood. We can deal with our machines, and we all are addicted to our machines. But that's because we symbolically know that that's representing communication with another person, or that's really a person in there. Little ones need people. Under 2, I don't recommend technology for children under the age of 2. Little ones need people, yeah.
Well, and isn't that part of the power of play?
It's the power of play, power of imitation, because kids get emotionally involved. And they love each other, meaning, you know, you watch babies in a room. If there were two babies in this ballroom, I swear they'd crawl to one another, you know, because that's a social other they understand. You know, our brains are built to operate on the basis of, I want to learn from something like me. And that like me attitude is the powerful learning drive. It's also, unfortunately, what creates stereotypes. You know, if you're a black child and you see, well, this is how this society treats black children, you begin to think, oh, well, that's how they're going to treat me. My husband is doing a lot of studies on stereotypes, on the idea that girls think they can't do science and mathematics. And he's demonstrated that, and he can see that it's through the social channel. If I don't see girls out there doing math and science, I'm going to think women don't like math or they're not good at math. I have a stereotype. Not true, but it becomes a belief. So he's shown that by age 2 or 3, you know whether you're a girl or a boy. And then by first grade, you've adopted the stereotype. Girls in this culture don't really like math. And by second, third grade, you start to think, well, then I don't like math. And so then my aspiration is I don't follow math. So the social channel is important for education writ large, that if we expect our citizens, men, women, to join STEM disciplines, and for race not to make a difference. Black kids shouldn't think they don't do math. Oh, Asians are good at math. Black kids aren't. The kids are walking around with stereotypes that limit their potential. And what we want to do is open those doors, open their potential. Let them cruise through the world without the biases of a label and find a passion for them. Because again, this notion that the social brain and the attention centers should lock on to something, and passion is what you want to look for in your young child.
Right. Yes.
All right. Thank you, Dr. Kuhl, for your amazing talk. We have one more question from the audience, and the question is, can you speak to the research that babies' cry patterns mimic the sing-song pattern of their parents' native language?
So babies' cry patterns mimic the prosody of their mother. Cries are really interesting. Cries have a kind of universal character. We've done a little bit of work, not published work, but a little bit of work across cultures looking at cry. And cry has a particular, you know, mothers will often tell you, I can tell whether she's in pain or whether she's hungry or what it is. That seems to be universal across cultures. And I haven't seen, I guess I couldn't verify that the cry pattern becomes something that mimics a tonal pattern of the language. I wouldn't be able to verify that. What I've seen is the kind of universal tendency for kids to cry in a particular way, and that parents get to be quite good at detecting what the cry means in the baby. Yeah.
All right. Any other, I'm looking, the lights. Yes, one more here.
Do we, with Madrid, have any statistics on the children graduating from, I guess, gymnasium there? You know, is the dropout rate much lower? Is the prison rate much lower? I mean, are we seeing that because they're all getting into preschool?
Yeah, it's interesting. So I don't know those statistics. I'm going to find them out. I mean, we just started in September, and the first cohort finished in February. We've been so busy getting data from Madrid every 2 weeks. We record the babies every 2 weeks to hear what are they babbling in Spanish or English. And when they get to the word stage, what words are they using? And what's happening to their Spanish as they learn English. So we have a set of beliefs about what's going to happen, but we want to know. So I think it's very interesting to think about whether bilingualism in general would make you, since your frontal cortex is better developed and you have better executive function, do you make better choices? You know, we've always linked reading. Look at the incarceration of people who can't read. How many problems would we solve if every child became a reader? Every child should be a reader. There's no reason unless there's a dyslexia. Dyslexia is a brain malfunction that makes it more difficult to read, and especially English. I mean, you can look at how easy the language is to penetrate and match up the dyslexia rate. So in Finland, for example, you hardly see any dyslexia because the phonics are so easy. Sound letter correspondences are just about 1-to-1. Very little dyslexia. And so you can stack up the complexity of the language and stack up the rate of dyslexia. And we have it, we're not good. English is hard. And so we have a lot of children with dyslexia. But in the absence of that problem, every child can read. We should solve that problem in this country. We're making a huge mistake if we don't.
Yeah. All right, our final question for the evening.
Good evening.
Hi.
Will you speak a little bit on about cortisol, why that's released and what function it plays,
Yes.
positive and negative?
Yeah, so I didn't spend very much time talking about toxic stress. When we get stressed, cortisol increases in our body. We could walk around all day if we had measurements of cortisol, and we would know it if we're sensitive to how we feel. You know when you're stressed. And cortisol would be a measure. If you're not keenly aware of your state, cortisol would increase. In the baby brain, babies who are stressed, chronically stressed, I don't mean a little stress. A little stress is good for all of us. But chronic stress, the kind of stress that comes from being abused or neglected, has a cycle of cortisol that just keeps flooding the brain. And what happens is that growth that I showed you, the growth of the brain as a whole, the synaptic growth, and then its flourishing and then pruning, all of that gets stunted when chronic stress is in play. Because the brain is not comfortable growing. The brain is trying to, fight or flight, right? Your sense when you're really scared is that you're either going to have to fight or you're going to have to flee. And so a child's brain doesn't have those concepts, but a child's brain is generating cortisol because cortisol is automatic. When you're stressed, it comes to the fore. So it's very unhealthy to be under chronic stress. And it is the antithesis of learning. The learning brain is a happy brain, a social brain, and a totally engaged brain, and a brain that's directing its attention, in love with what's happening and really trying to explore it. Under cortisol, you're exploring nothing. You're not happy. In fact, you're the opposite. And you notice how when you're stressed, you drop your keys, you can't get your door open, you can't do it, you drop everything. It's because your brain is rattled and your brain's fully formed. But if that kind of rattling happens when you're trying to form a brain, when you're trying to build a brain, you're in deep trouble. So kids who are under chronic stress, one of the biggest pieces of evidence is the lack of executive function, the lack of the ability to control your impulses, the lack of the ability to direct your attention where you want it to be and hold it there. And we think it's because the cortisol has gotten in the way. The activities that would help you train executive function haven't been there. And so you're at wit's end. And so you are impulsive. And what we don't know is how much of that stress could you have as a baby and still recover? That's what we don't know. So you can't run that experiment, right? We just know that kids the more stress they're under, we've got a study underway right now that'll be very interesting. The kids are 5, and the one group's been in foster care, now is in a family, in a foster care family, not with their biological parents. And the other control group is matched really carefully with each foster child on every dimension that we could think of. And we're trying to just look at the global brain. What has it done to your brain at age 5 to have been in the foster care system? That means that the abuse and neglect was so bad, you had to be taken from your biological parents. And so we're trying to look at variables like when were you taken from the family? How does that predict, how much did you have to endure? So that's the way we're going about it, and we don't have the result yet. All the data are collected, it's now being analyzed. We're expecting a very dramatic difference between those brains particularly in prefrontal cortex. But we'll have to wait and see. I think people need images. I think it's going to be good for us to see those images because we need to see. Just remember how much we learned from looking at the black lung commercial. Here's your lungs on smoke. Okay, did you want to smoke after that? No, right? And the crash dummies, here's why you hook up your seatbelt, because this is what happens to your head if you don't. We need the same thing for your brain. Here's your brain on stress. Here's the baby brain on stress. Here's the baby brain on happiness and social interaction with loving parents. We need those images. I think that's part of what the brain studies are doing for us.
Wow. So we just want to thank you again
you're welcome.
for
You're
a
such a wonderful
fascinating
audience.
evening, and we look so forward to watching all of your work and learning more the next
Well,
time.
good. Thank you.
come.
You're doing wonderful work here. We're going to keep watching you. So
great.
keep leading the way here in California.
Please help thank her again. Great. So the only other thing I'm supposed to do is remind you that we're starting at 9 a.m. So get your coffee early so you can get a good seat, and we will see you all here in the morning. Thank you so much, everyone.